my screen and we'll get going. Okay, so yes, the talk is about spatial clustering with the example of deaths in Scotland. I'd like to start with an introduction, a brief introduction to what we consider as spatial epidemiology. I'll go on to talk about some well-known and some lesser-known examples of historical examples of disease mapping, and then go on to how we can define the degree of clustering and detecting clusters in point and areal data. We'll have a break of 5 minutes so we can get a cup of coffee, and then we'll be looking at the example using R and the Scottish aggregated death data. So I sent around a couple of papers which I feel are a really good summary of the sub-discipline. The first by Rizaian looks at some of the terminology that's used, so how we define points, how we define areas, areal units. Some of the key concepts such as spatial autocorrelation, the modifiable areal unit problem, and so forth. So hopefully that gave you some basis for some of the things we're going to talk about today. And the second one was really, yeah, a kind of a blueprint for what has been going on in spatial epidemiology. This was an older paper from 2004, and some of the kind of challenges that were faced at that time point. And really what that paper showed was that spatial epidemiology is really 3 lines of inquiry, and they kind of flow into each other. So they go from disease mapping, spatial clustering, to geographic correlation. So we're going to be talking about spatial clustering today. The next seminar is on geographic correlation. So there's a lot today that we'll learn about that will be important for the next session. So just to, I'm probably sure that you've all heard of this example. It's the famous John Snow, who is often termed as the father of epidemiology. He produced this map of cholera deaths in the 1850s when there was an epidemic.
Mark,
yes?
Mark, sorry, can I interrupt? Your screen is not progressing.
Oh, is it not?
Yeah, so can you, is it showing normally on your screen?
Yes, yeah.
Are you sharing your screen? All right.
Yes.
Are you on slideshow mode or just normal mode?
I was on slideshow.
I think you might be showing, because what we're seeing is the normal.
The first. Oh.
Yeah, if you put it on slideshow again, can you just do it right now and then let's see if it's working?
Right. Okay. So yeah, you've probably all heard of this, so I don't want to spend too much time. But the black bars are showing you cholera deaths, and you know this was an important example because at the time they thought that cholera was transmitted via bad air or miasma, and John Snow developed this map because he had an inclination that it was waterborne. And you can see that there is, you know, higher number of deaths around the Broad Street, and in particular, the pump. So this was, you know, acted upon, and you know, the handle was taken off the pump, the water supply taken away, and there was a reduction in the cases and deaths thereafter. So another kind of important side of this that maybe isn't talked about as much is that John Snow was really keen on trying to understand the spatial outliers. So there's a workhouse just to the north where a lot of people frequented. You might have expected a larger number of deaths to be from there. actually found out that they did have their own water supply, so that explained that outlier. There was another case of Susanna Ely, which she lived way outside this region in Hampshire, I think. And he also did some investigations into why she died of cholera. And it turned out that she was actually getting barrels and barrels worth of water delivered to her house because she preferred the taste of the water from this pump. So that was the reason behind that spatial outlier as well. So I thought probably you all have heard of that example, but one that you might not have heard of is the, which happened around the same time period, was in Edinburgh. And it was created by Dr. Robert Phillip. He mapped the tuberculosis cases, the first 1,000 for Edinburgh, and he produced this map on the right here. So the red dots are where we see a case of tuberculosis. And yeah, I just thought to begin with, it would be nice to just, hopefully you've never seen this map before, and you know, I think it's a nice example of disease mapping. If we could spend a couple of minutes just thinking about what the pattern is showing on the map, if there are any clues to explain this pattern from what you can see, and what other sources of information you might use to understand that pattern. So I realized that map's quite small for your screen, so if you you can go to this link and you can see a bigger version which you can zoom into. If you want some spoilers for what's going on, then you can read about this case in the it was in the Edinburgh News Scotsman just in March. But yeah, if you can have a think about that now, and just unmute yourself and say what you think. And if not, I'll just talk about it.
Mark, it looks like the dots follow roads.
Yeah, so that's an interesting point about this map, in that Robert Phillip took the decision to preserve the confidentiality of the people by not putting the dot on their homes, but actually on the road. So that was a kind of deliberate decision to try and not allow the people that had died to be identified. In terms of the spatial pattern, I guess what we can see here is that there's a northwest and a southeast gradient. So the northwest of the city has much fewer cases compared to the south east. Some of the things that I picked up on were the building density. You can see that actually the dots are in areas that are have a very high density of buildings. The road structure is quite higgledy-piggledy compared to you know, the northwest, where there's much more kind of gridded area with much more open spaces. And I guess if you know Edinburgh, you know that corresponds to the old town and the new town. So yeah, I guess starting to build up a picture on why there might be higher number of cases there, whether it might be overcrowding, yeah, high density of people. So we might suspect that it's got something to do with socioeconomic status. You can see that the railway line through Edinburgh cuts the kind of pattern quite well, actually. So it goes, you know, right through the centre. And railway lines, I guess, are commonly commonly seen to differentiate between higher and lower socioeconomically deprived areas and cities. In terms of information that could be collected, well, if we followed the kind of way that Robert Phillip did, he collected all the occupations for the people that had died, and so that was, we might see from the from here, we might think that it's a socioeconomic pattern, but actually you can confirm it with when we know the occupations. And actually, what he found was that it was prevalent in quite a cross section of society at that time. Quite a range of jobs, not just the more manual classes. So that was good to kind of confirm some of the suspicions that we have in this map. So those are two historical examples. To go now to a broad definition of what I mean by spatial clustering. It's a higher or lower expected set of events in time and space. And there's a number of ways that we can detect clustering. So we can use a density-based approach or a distance-based approach. And really that, in mathematical terms, it's corresponding to the first order property and the second order property. So the first order property being the distribution of points within an area, the second order being the relationship between the points. We're going to concentrate on the density-based side today. If you want to learn more about distance-based, it's a good introduction to that is the nearest neighbor analysis, and using R, there's a number of packages that you can use to do those. So in terms of density, the kind of most simple way to understand the degree of clustering in a region is to look at the global density. So we've got 60 deaths here in an area, say it's 2 kilometers squared. So we've got 30 deaths per kilometer square. But we're often interested in local density. So really, are we seeing the same kind of uniform level of clustering in different areas? So this is the same deaths, same region, but actually just cut up into 3 areas. And we can apply an analysis called Quadrat analysis, where we divide the areas into boxes, and then we calculate the number of deaths in each quadrat or box. And then we compare it to what we would expect in that box given a certain distribution. So it tends to be the Poisson distribution that we would use. So the formula, so we can see that there are, within that global area, there are 3 patterns. We've got a random pattern, a uniform pattern, and a clustered pattern. So how do we know whether that's clustered or not? Well, we can do a test. We can calculate the chi-squared test statistic. So the formula is below there. So we take the observed number in each quadrat, we minus what we'd expect there, we square it and then divide by the expected. We sum that up and we get that chi-squared test statistic. So in the case of the one on the far right, the clustered version, it's 80. We then compare that to a critical values table. And the 2 important parts there are the alpha and the degrees of freedom. The alpha will be determined on what level of significance you want to have. So it could be 0.01, 0.05. They're commonly used. And it'll also be the degrees of freedom. So that'll be determined by the number of quadrats minus 1. So for the example on the clustered side, we see that it's significant to 0.0001, meaning that there's a 1 in 1,000 chance of this pattern being observed under the assumption that it's a random pattern. Okay. But one of the limitations of this method is that it's very sensitive to the Quadrat size. So we might have quadrats that are too small, so we've got lots of 0 points, and they could be too big, so they're kind of obscuring the clustering because there's the same number of points in each quadrat. And there are ways to kind of try to get to the optimal Quadrat size, but what this is a really good example of the modifiable areal unit problem. So the scale of our analysis will have an effect on what kind of clustering we see, what kind of inference we can take from that analysis. One of the ways to get around that, keeping with a localized density approach, is to undertake a kernel density estimate. So this computes a surface across the study area which isn't constrained by boundaries. So this is what you would usually do here is create a grid over your points and for the extent of your study area. That'll be you will define the cell size. So the smaller the cell, the smoother the surface. The bigger the cell, the kind of more uneven you'd get that. And for each centroid of the grid cells, you're calculating the density. And you're calculating that density based on a kernel which is fitted to each point. And the kernel can be a number of different types. So most commonly used is the Gaussian. And that kind of shows you how much the point can spread around into the other, into the cells around it. And then what you do is just take the sum of the fraction of the points for each of the cells. More importantly than the type of kernel is actually the bandwidth size or the radius, so how far you expect a point to kind of influence. So, for example, some of the previous times that I've done this, it's been with retailers, and so we've used a distance that corresponds to around a 5-10 minute walk. So the bandwidth is very important to consider here. And really in the end, kernel density gives you is a proximity weighted estimate of the density. So that's, if you want to explore more on the spatial KDE, there is a package in R which was just developed a couple of months ago. Previously, the way I've done it is that you leverage a GIS from R. So you would kind of send your commands to Saga GIS or QGIS, and then you would take back the results from that and plug them back into R. I guess the kind of next steps in terms of looking at point pattern are methods such as the geographical analysis machine. So this is an automated way to detect clusters. And then going on to methods such as dbScan and SATscan. Again, there's R packages that you can leverage for those. If you're not keen to kind of go into the R side of things to begin with, there's a paper there at the bottom that uses SATscan. I think the methods are really well described, and it's a really good example of the utility of trying to uncover clusters in space and time and how they relate to inequalities. So that's where we were talking about points, but a lot of the time we don't actually have point data. We need to aggregate the data at area levels to preserve confidentiality. So there's a good paper on how published maps from Hurricane Katrina were kind of digitized and actually could then identify people that had died during that event. One of the advantages of this aggregation is that you can then provide evidence at the appropriate level, social, economic, and political level. There's a number of ways that aggregated data can be represented. It can be a count, accrued count, it could be accrued rate, so it's divided by the population, or the one I want to talk about a bit more is the standardized rate. So there's two types of standardization. Standardization is a good way to account for the structure of the population that might influence the count. So, for mortality, the risk is obviously higher as you get older, and also there's certain kind of diseases that will affect one of the sexes more than others. So certain types of cancer will affect, so breast cancer will affect women, testicular cancer will affect men, for example. And we can use standardization to get around the fact that we've got different age sex structure in different small areas. So the two common ones are direct, where you take the age sex rate of the study and apply those to a standard population. So a standard population could be European or UK or the world, for example. The indirect is where you take the age sex rate for the standard population and then you apply that to how many people are actually in your small areas. So the indirect is commonly used and is one that we'll be using in our example. So I thought it would be good to just kind of go over the calculation. So we're looking at what we'd observe divided by what we'd expect to get a measure called the standardized mortality ratio. So yeah, this is the formula where you sum all the observed deaths in the area and you divide that by the age sex specific rates that are from your standard, multiplied by the population in your area that correspond to those. And what you get at the end of that is a number that where 100 corresponds to equal amount of observed deaths to what you would expect, and anything over is more observed deaths than you would expect. So a standardized mortality ratio of 170, for example, would be 70% more deaths than you'd expect. So in terms of clustering this areal data, we can use a way of doing that called spatial autocorrelation. And this is slightly different from the other ones that we've been talking about so far. It's not just based on the location, it's also based on the values. So spatial autocorrelation is the kind of association of values that are in close proximity to each other. And we do that by, first of all, defining what neighbours an area has. So this is commonly called a contiguity matrix or a neighbourhood matrix. And you can define it by different chess moves. So bishop, rook, or queen. So for the bishop, the neighbours would be the first, the third, the seventh, and the ninth. It can be, you can also define whether you want the immediate neighbours or neighbours of neighbours. So that's also another consideration. So the formula for, so the way to define spatial autocorrelation in aerial data is there's a number of statistics, but one of them is Moran's I. The calculation is shown here, and it looks slightly daunting, but really it's, we can go through it in this example that's shown here. So if you look on the left-hand side, we've got 6 areas that have their standardized mortality ratio. So this area here, B, has got 150, so it's 50% more deaths than would be expected. In F, you've got 50 as the SMR, so you've got 50% less deaths than you would expect. The first thing to do is to look at the neighbourhood matrix. So we've got the areas along the columns here and along the rows. And what we're doing is we're just identifying the neighbours by placing a 0 or a 1. So A borders B and C, so we put a 1 in B and C. B borders A, C, and D, so we put a 1 in A, C, and D, and so on. So this first step can get you the first part of the calculation, so you can get the W and the N. So the N is the number of units, so there's 6, and the W is the number of neighbours. So you just count up all the ones, which gives you 18. On to step 2. We are now interested in this part. So for every area, we're taking what we observed there from the mean. So the mean we've calculated based on all these numbers is 101.6667. So we calculate the difference between the observed and the mean, and these are shown here. We then square it to get this part, and then we take the sum, which is 8,283. So now we've got these two parts of the equation as well. Step 3 is to bring this bit together. So we've got our data here that we'll need in this column. We create a matrix with I and J, which are the A to F, and J will be A to F going down on the rows. And we just multiply, this is this bit here, we just multiply the I multiplied by the J. So and for this one here, we're multiplying A by B, so it's 38 times 48, and that gives you 1,852. This part here is the where you apply the weights and then you sum the results. So because we've got, if we look back, we've got zeros and ones as our neighbourhood weights. So we're just taking 0 times 0, 1 times this, 1 times this. I mean, if you construct the weights matrix differently, you might have non-integer values there, but because it's an aerial model, you get the ones and zeros. So it's really quite an easy calculation there. So all you're doing is then summing each of these, summing all of these together, which gives you 6,193. And the final step is then to bring it together. So we've got our 6 divided by 18 in the first step, and the second 2 steps, step 2 and step 3, give us 6,194 divided by 8,283, and that gives us a Moran's I value of 0.25, which is showing positive spatial autocorrelation. So the Moran's I, it varies, it ranges from -1 to 1. So 1 would be complete positive spatial correlation, as we see here, and -1 would be complete negative spatial autocorrelation. with no correlation, looking like the middle square there. So if that's kind of clear, I thought we could just spend a couple of minutes again, you know, just having a think about features of the urban environment that would display positive and negative spatial autocorrelation. Yeah, and then so if anyone wants to talk about their examples, you know, in terms of yeah, what they think, then that would be great. If not, I'll talk about mine.
How about nitrogen dioxide and cars in busy streets?
Yep. Any other environmental ones, or physical environment?
Building density and population?
As positive.
Positive, yeah.
Yep.
Negative, maybe green space and like parks and air pollution.
Yep. Yeah, parks, definitely. Other ones, like cinemas, hospitals, often negative.
Mm-hmm.
Good, all right. Cool, okay. I've now got, I thought we could have a break to get a coffee before we go on to the next part, which is the R part. I have put all the code up on GitHub, and it's on this, from this link here. If you want to go along with the code, then if you want to clone that repository, and then if you run the setup.r, that'll download all the packages that you need for this analysis.
Can you copy that into the chat box just so people can more easily get it?
Right. Theory part of the presentation. Okay. Has anyone cloned the repository? I wasn't sure whether people would, would be using R, so I've kind of gone with the option of just, yeah, I'll explain all the code, so you can go through it with me at the same time. But yeah, I didn't know everyone's set up, so I thought it'd be better to just do it this way. Okay, right. So this is a way of designing a cluster analysis. This would be your workflow. First of all, collecting information, on mortality, doing a pre-processing script to get it all formatted, feeding that data into an algorithm, cluster algorithm, and then looking at the results and interpreting them. And that's a kind of iterative kind of loop where you'd be modifying the parameters and then seeing if it's a good model to go with, and then you would have useful information at the end, hopefully. So the motivating example is using Scottish death data. The question is whether there is evidence of clustering in small areas in Scotland. And if so, how has that changed recently? So we're using the SMR indicator that we talked about in the first session. This is using data on 5-year age bands and sex. It's, as you know, the SMR is indirectly standardized, and it's using the Scottish population as the standard. You can see here that, well, the data that we're going to be using is from 2016 and 2020, but actually that data, it's actually from an earlier period, but the product is called the SIMD, the Scottish Index of Multiple Deprivation, and it's for 2016 and 20. So in terms of getting that data into R, we're first of all, we're doing that pre-processing. So we've identified our data that we want to use, and then we're going into the pre-processing script. So we're using a package called Reader and a package called SF. SF stands for Simple Features, which is a way of representing geographic data to, it's an ISO standard. So if you might have heard of it before, there's ways of representing geographic information such as well-known text or well-known binary text. So SF has all those kind of ways that you can read in the data for that. And we're using a function called read_SF. What's nice about that is that if you provide an extension .shp, it will automatically use the correct driver. In the kind of other way of doing this in R, you'd use OGR, and you have to specify a lot more information. So SF is a really kind of quite a neat new package that makes it easier to work with geographic data. At the moment, it's only aerial data that you can work on with SF, so it's worth bearing in mind that. So basically we're reading in the boundaries that our SMR data corresponds to. So these are Scottish data zones. So there's around 7,000 in Scotland. So they're quite a small geographic unit. Next, we're reading in the SIMD data using the reader package, the read_CSV function. And the next part is to use dplyr, which is a really great package for data wrangling. And dplyr works on the way it works is by using pipes. So the pipe is percentage sign and then a forward arrow and a percentage sign. So that's a pipe. What pipe does is it takes the output of the left-hand side of the pipe and it puts it into the next part, as a pipe would do. So what we're doing here is we're taking that spatial boundary file, and we're using a left join, so that's a merge function. So we're merging the SIMD data, and we're merging it on the column of the code for the data zone. And unfortunately, that code is spelled differently between the two data sets here. So we need to just put in this little bit of code that says that if you know, data zone with and without the underscore they correspond to the same thing. So once we've done that, we've now got these two together, and we want to pipe that object into another function called filter. And what filter does is it subsets the data. So one of the limitations of spatial autocorrelation analysis and creating a neighbourhood matrix is that it's very computer intensive. So in this example, I wanted to concentrate on Glasgow. Glasgow's a good case to look at mortality because it is a place which has kind of traditionally had an excess mortality compared to places of a similar socioeconomic level. You know, it's often in the literature called the Glasgow effect, that kind of reason why it's excess mortality. So we're subsetting this data set just to Glasgow, and then we're piping that into two functions. These are mutate is a function that's used to generate a new variable. So we want to just do some formatting on that SMR variable to make sure that it's a numeric variable. And then we are getting rid of the, there's two data zones that are missing. And we're just using a crude approach to fill in that missing data by taking the median of all the Glasgow area. So you know, you probably want to do something a bit more sophisticated than that in a real application, but just, you know, for the purposes of today, it's fine. And finally, we just want to kind of make our data set a bit more manageable. So we're only selecting columns. We're only selecting 3 columns, and those are the data zone code, the name of the data zone, and the SMR value. Right, so once we've done that, we can now get a picture of Glasgow with the SMR data. So the SF package is really good because it kind of hijacks the kind of generic functions in R. So it allows you just to use R's plotting function as it is, and you get a really quick result. So all we have done here is taken our new, I've assigned it to a new object there called data zone DZ_SIMD. And all we're doing there is plotting that object, and the attribute that we're interested in is the SMR. If you didn't put that there, it would give you a map of the, it would give you 3 maps. So it would give you the code and the name and the SMR, and it would try and color that categorical data for the first 2 in a way that it thought was useful. But one of the limitations of this kind of plot is really nice to get something really quick, but obviously, you know, it just gives you a continuous scale. So, you know, from this we can only see that it's the west and the east that are really high in their SMR. A better way to look at the kind of pattern that we're seeing is to use another function called tmap. So tmap has 2 modes that you can set by using this function called tmap_mode. So first of all, we want to just plot it. We want to get a graphic out that we can put in a paper. We set it as the plot mode. All this is doing then is creating an object called creating a tmap object, and you're specifying that you know, that previous object that we built is what you'd like your shapes to represent, and you're going to fill them in with that attribute. Crucially, the difference between the previous plot and this one is that you can say that you want the values to be grouped by quantile, and we could change the palette as well. So we can change the colors to make them show that kind of continuous increase. Probably, you know, a little bit better than the divergent palette that was default in the last slide. We then just do some kind of making it pretty. by changing the transparency of the borders and then giving it a title and different things. And then we can plot that object by running just entering the object in, and this is where we get this map here. So a much better visualization of where we're seeing the highest levels of SMR, not just the two that we saw in the previous map. I said that there's two modes. So the other mode is the view mode, and that's really nice in that it gives you an interactive map. So you might actually want to kind of zoom into this area here, where you see that there's higher area surrounded by lower areas, and you can also change the background map. So at the moment it's using an Esri map, but you can use OpenStreetMap. So you might want to try and understand what features in the urban environment are associated with the excess deaths. So actually seeing it on a contemporary map, you could use Google, for example, as well, is really quite useful. So that's a good thing to remember as well. So the good thing about visualization at this stage as well is just to make sure that you've actually read in the data correctly. There's no really kind of spurious things that is going on with the way that you formatted it. So it's a good check to make sure that your code's running correctly so far. Onto now doing the neighbourhood structure or the contiguity matrix. Luckily, you don't need to do this by hand. You don't need to look at all the areas and then decide which are neighbours and which are not. There's a couple of packages that help with this. They are SP and SPDEP. I said that the SF package was new, and that means that a lot of these older functions don't actually work with SF objects. So we need to change it into an SP object so that we can use it with SP functions. I suspect in time this is probably going to, you won't need to do this because they probably kind of port all the old functions to the new. But at the moment, it's important to remember that it won't work with your normal SF object. We use a poly to NB function to construct the neighbors list. So that's just doing that that matrix that I showed you earlier with the A to F. That's all that it's doing there, and we can get a really nice summary of what has taken place. So in our Glasgow example, we can see that the number of regions are 700. Sorry, the number of data zones are 746. We can see that there's a number that the number of neighbours is 4,310, and the average number of neighbours is around 6. It also gives us the distribution. So this means that there's 2 data zones that have 1 neighbour, 12 data zones that have 2 neighbours, 64 data zones that have 3 neighbours, and so on. So there's one data zone, one area that has 18 neighbours, but you can see that most are around that 5 and 6. Give it, and that obviously corresponds to the average. Quite useful as well. It gives you the code for the least connected neighbour and the most connected, most connected data zone. Sorry, the least connected data zone and the most connected data zone, so you can kind of have a look at, where they are. Again, it's good to visualize to see what's actually going on under the hood, and for this we use the kind of generic plotting function. So all we're doing here is saying we want to plot the boundaries in grey. We then want to get the centroid of each of those boundaries, and then we use that weights object that we just produced and we're plotting the link between the weights object and that centroid. And we're coloring it red, and we're adding it to that previous plot that we just made. So yeah, I think it's good to know. I mean, the whole thing about spatial autocorrelation is dependent on the how you define the neighborhood structure. So it's often really good to kind of interrogate this, and we'll pick up a bit on that later on. But you can see there that there's one of the two data zones that only has one neighbor, right at the south there. Okay, next we want to calculate Moran's I, like we did manually previously, and you know, for this we use so for this we need to have it in a certain format. We need it in a list, so we use this list function, and this is the command that we would run for Moran's I. We yeah, we're specifying the attribute, the number of the length of the weights matrix, and then this is the number of neighbors. So this one corresponds to the 4,310 that we talked about earlier. So this time we have again spatial autocorrelation of 0.18. So we can say that it's positive. There is a degree of clustering, but we want to know whether that's statistically significant. So for that, we need to use Monte Carlo methods. First of all, we set the seed. So that will make sure that if you run this again, you'll get the same result. Otherwise, if you don't, you know, you'll constantly be getting a different results. And we take 1,000 simulations of this SMR value, and we get this. When we plot the result, we get the distribution that you see here, and we can see with the line where our Moran's I value sits. So it's way off into the tail of the distribution, and it also outputs a p-value. So we can see that this clustering has a highly significant. It's highly significant. Okay, so once we know that we've got global spatial autocorrelation, we're then interested in how that is, yeah, like we've said with the density, and like we've said with in the manual calculation, we want to know how that is then that plays out in a local context, and that's where you use the Moran's plot. It's a good way to visualize what's going on in the next stage. So what you're seeing here is the observed SMR value, and then you've got the spatially lagged SMR value. So the spatially lagged is the average for the neighbors of that unit, and so the line is showing you the global spatial autocorrelation. So that's the 0.18. That's the 0.18 I number there. But you can see all the individual points where they lie on that on the graph. And why that's important is because you can then divide up the Moran's I into 4 sections. So the red section is an area where you've got high observed and you've got high surrounding. So that's a cluster of high. That's the terminology that's used. Down in the bottom left, you've got a cluster of low. So low in the area and low surrounding. And then you've got the spatial outliers. So you've got areas that are high, but are actually surrounded by low areas. And then you've got areas that are low, but actually they're surrounded by high areas. And that's really what we do to look at the local indicator spatial autocorrelation as spatial association. We we decompose the global spatial autocorrelation by those segments. But crucially, we also want to know whether they're significant. So we run the local Moran function for the for each unit, and we get a p-value for each area. So that's important as well for the next part. The final bit is just to scale the SMR, and we do that so that we can we don't need to hard code the absolute values of SMR. This will become apparent in the next slide. So this slide is showing how we take what we've done in the last two bits of code and we apply it to get areas that are significantly high, significantly low, and the high-low and low-high. So that's what I meant by the fact. So this is an if else statement. So again, we're using dplyr to pipe the object and then generate a variable that's called the quadrant significance. So that's the area, the floor area significance. And we're using the if else statement to define a criteria that means that this is a high cluster. So the reason that it was scaled before was that if we didn't scale it, it would mean that we'd have to change that value to, whatever was appropriate for, based on this slide. We'd have to change it to this value here. So scaling it means that this code would run for a different data set, a different year, like we're going to do later on. So it's really important to do that. And just like I said before, we're just doing the criteria. We just define that criteria based on the plot. And we're using a significance level of 0.05, and we're taking that from that object that we just created that gives you the significance for each area. So I hope that makes sense. This is kind of the most complicated part of it, I think. When we've got all that, we can then create a 𝗀𝗲𝘁𝗶𝐵 map with that new object, and we're using that new variable to show the clusters. We can also do a summary of what actually, how many of high, how many low that we get in our data set. Okay, so this is the result. We get to see that there are areas of high surrounded by high areas. There are clusters of areas that are low surrounded by low areas. And it looks like they're quite spread out towards the outskirts of Glasgow. When we can do that for different time periods, the assumption is that the data collection has been done in the same way, which I think is fair for this kind of data. All-cause mortality. You might have more issues if you're actually using a single disease, or if you're looking at very long periods of time between your two time points. But because we're talking about a 5-10 year difference, it's not it doesn't seem to be such an issue. And what we can see is that there does seem to be more areas of high clusters in Glasgow and low clusters. As we kind of progress from 2016 to 20, data from 2016 to 20. And we also get a non-significant in grey, so we can see where we haven't been able to detect clusters with the pre-specified level of significance. And what we can do, I've not shown the code for this, but it's very similar to the if else statement. The code is in the GitHub if you want to have a go at doing this. And it's basically just showing, we're using the FL statement to show where places have changed and where they've not. So between the two maps, these are, in 2016, these areas were not significant, and now they're high clusters, and the same with the other red. So it's a good way of showing the kind of change over time. So in summary, we identified a mortality dataset that was available at a small area level. The advantage was that it was standardized by age and sex, and it was at two time points, and we felt that there wasn't a huge discrepancy in the kind of data collection methods between those, so we can compare between them. We processed a sub-region, that was Glasgow, and we created a neighbourhood contiguity matrix, and that enabled us to run the Moran's I, which is our clustering algorithm. We got our results, which we decomposed to identify clusters. So we could then start to interpret those. But before we go on to whether that is useful information, we need to see whether there's utility in modifying the parameters. You know, I mentioned before, one of the key bits of this is that you know, it's very sensitive to the neighbourhood matrix. So you really need to be confident that this is the best way of representing the relationship between the units. So, you know, for example, we've got the River Clyde that runs right through the centre of Glasgow, and it divides, we can't see any neighbours between those north and south of the river, sorry, the estuary. So we might want to look at, you know, whether if there's bridges, you know, these areas might actually be connected, and we might want to specify that in the model. So we can do that manually, or there is a function which I've put in the code as well. It's called snapping, where you can snap the boundary to a certain level. So it would be a good idea to perform sensitivity analysis with these different assumptions on the neighbourhood matrix, and really it's trial and error to get the correct one. So just to give an overview of what we've done today, we've looked at the kind of key lines of inquiry for spatial epidemiology, concentrating on clustering. We've had a look at some historical examples of disease mapping and how that was used to instigate ideas of clustering, both well-known and lesser well-known. So you could say, hopefully that, you know, this is one that people haven't heard of. And we've talked about the two data types and how you would define clustering and detect clusters in each. We're really concentrated on the areal side for our example. So on that example, I've kind of assumed that you use R at the moment, but if not, there are a number of online books that I find really useful for GIS, for geocomputation, and for data science in general. So I really recommend having a look at these, and hopefully, you know, if get you up to speed on kind of R for this work. But if you're not interested in R for data analysis, but you do want to do this kind of work, there's a really good GUI which is called Geoda, and you can replicate a lot of what we've done today. I guess R just gives you that flexibility to change things. So yeah, it's worth it's yeah, it's a good thing to start with, but perhaps you know, as you go on, R would give you that greater flexibility. So as I said, you know, some of you might have been going through the R code already. If not, you can get it from that link. And what you need to do is just clone that repository, you run the setup code. What I've done is I've actually put on we talked about COVID at the start of the seminar. What I've done is I've put the code for COVID death that was released by the NRS at the intermediate zone level. I've put that data up online, and you know, one of the things that you might consider doing is modifying the code that we've used for the all-cause mortality to look at the COVID deaths. And I think that's it would be a really useful piece of analysis, because you might find evidence of what's being talked about in the literature as a syndemic. So this is a paper that was published recently by 𝗀𝗲𝘁𝗶𝗹, talking about how COVID-19 is kind of intertwined with the social determinants of health, is intertwined with inequalities in morbidity and mortality. So really what the question is whether we see the same clusters in all-cause mortality as we do with the COVID-19 pandemic. So the data is up there for you to answer that question. So that's everything today. Please get in touch with me if you've got any questions about the analysis or any of the theory. Yeah, and my GitHub is there, so if you just want to clone the repository and then you can work on it and then push it back to me, that would be really good. So thanks a lot, and if there's any questions, I'm happy to take them now or whenever you feel ready.
Great. Thank you very much, Mark. Very interesting presentation, both the theoretical parts, the small literature review, and more interesting the step-by-step explanation of the code for us to replicate basically the spatial clustering techniques we have showed us. Also, the last part looks very interesting as you try to relate it with the COVID-19 spatial spread of the disease. So that would be an interesting task to perform.
Yeah.
Are there any questions, any comments from our audience?
Yes. Can you hear me?
Yes.
Yes. Good afternoon, everyone, and thank you for the wonderful presentation.
Oh, good.
Can you hear me?
Oh, yes, yes.
Yes, okay. So 2 weeks ago, out of curiosity, I bumped into StatScan and an article using StatScan for the distribution of the COVID-19 cases in the States.
Yeah.
So as I understood from the article, it relies on Poisson distribution.
Yeah.
In a given time interval. Does it, theoretically, does it follow the same Moran's calculation, etc., or it's a different interpretation, or
Yeah, it's a little bit different. I haven't used it myself, but so that paper by McDonald is really good. Obviously it's looking at retailers, but it's good to you know, to really show the methods. My understanding of it is that it draws circles, kind of a number of circles around the areas and compares within and outside the circle based on what you observe and expect given a certain distribution.
yes.
So and it does that in space and time as well. So it's yeah, it's slightly different to what we've been talking about today, but it is a density-based measure.
Okay.
So it's just the way that they've it's just the way that it's the shape of the circle and the number of circles rather than the quadrat. It's kind of an extension of that. So.
Okay, because actually we found interesting results. We couldn't go to the lowest geographical area because of the lack of data. But what we found as clusters of high risk were actually clusters where we usually find outbreaks of communicable disease, such as measles, acute watery diarrhea, etc. So that was interesting, but we would like to go further with this interpretation. We're just challenged by the lack of data at lowest geographical level, but we will try to push things forward, because these were areas where we have like crowding index and low socioeconomic status, etc., and many determinants of health, like just what you mentioned in the last few slides. So that was something that we were seeing as well, but we didn't go that much yet into details.
Cool. Yeah. Have you got a preprint or publication for that analysis?
No, not yet, because actually I was asked to do this out of an exercise to find the dispersion factor. But when I tried this on my own, I wanted to go to get further details at lowest geographical area. That wasn't a priority anymore. So now I want to do this on my own, but now I know that I can ask you for help.
Yeah, be very interested in, very interested in that.
Yes.
Sounds good.
Because actually we can, the software says that we can layer other environmental data. I didn't know how to do that, but it would be a way to explore like the history or the historical data of communicable disease that we have. So thank you very much.
Sounds great. Yeah.
Thank you. Thank you, Nadine, for the nice comment. Anybody else? Questions or comments? Let me ask you also, Mark, a comment more on the implications of these analyses. And at a more practical level, is this kind of analysis actually used at the regulatory level to monitor clusters of death or other kinds of disease morbidity clusters? Or it's more at a research level?
Yeah, I think it's these techniques are, especially the automated ones, are certainly very useful for surveillance, like you mentioned. I don't know if the Scottish Government anyway are doing this on a continuous basis, but a lot of the methods that we've talked about today, they kind of feed into geographic correlation studies, and that is definitely very policy relevant, and also is done in a lot of research. So yeah, no, I think it's I haven't got examples to hand of these kind of surveillance, but I definitely will look into that. That's good. Good question. Thanks.
If I can expand a little bit my comment. So we are going to have also another webinar by you, which is actually going to be a continuation of today's analysis, trying to go more into, let's say, determinants of the clustering of death, for example. That would be also interesting to know, and that would be also very interesting to show for the next time. I just wanted to bring this up for the attention of everybody, so they can look forward to it as well.
Yeah, I'm looking forward to it as well. Yeah.
Of course, this one will take place, you know, after August, maybe September, but still. So, any last? I see it's already 4:30 here in Cyprus. Are there any last question or comments?
Yes, hi.
Hello.
Thank you for the presentation. In the pre-processing step you say for the NAs, you choose to fill in the NAs actually with the median.
Yeah.
Why did you choose median and not? Why did you choose median and not mean?
Oh, well, I guess it wasn't really, you know, I guess I just took the kind of central, a measure of the center of the average of the data. Yeah, it wasn't a really kind of deliberate decision. I don't think this is the best way to really deal with missing data. I mean, the fact there were so few areas that were missing probably, you know, means that it's not too much of an issue. Yeah.
You said that you had only 2 missing values.
Yeah.
So will you choose something different if you have more? If you had more NAs?
Yeah, I think you know, I tend to use the rule of thumb. If it's over 10% missing, there's cause for concern. With, you know, you need to really think about the missing data structure, and you know, you might try and do some kind of multiple imputation to model what you'd expect there, given a certain number of auxiliary variables. Yeah, and I think the best thing to do here would be to do sensitivity with different methods. I think yeah, if you've got a lot of missing data, then you should really be looking a bit more at the structure of it and modeling it better than I've done here. Because it's so few, I don't know if it's, yeah, it would be good to see whether it has a difference between the mean and the median, and in this case, but I doubt it will do. Yeah.
Okay, thank you.
Thanks for your question.
A last short question, comment? If not, then we're going to thank Dr. Mark Cherrie for his nice presentation. You're actually the last presenter for the academic year.
Okay.
So, and you will be the first one for the new academic year when we come back from the holidays. So I'm going to wish a great summer for everybody and stay safe. Thank you.
Have a great summer.